So one of the things we haven't been able to do yet this semester is we've looked at a number of sequences which we would, I think, all agree are not actually convergent sequences. And yet they still seem to have some kind of nice behavior embedded within them, such that we'd like to be able to say something convergent-like about them. So the sequence we're looking at on the screen here is the sequence whose formula is Sn is n times minus 1 to the n over n plus 1. So here's the first term in that sequence. Here's the second term, S2, S3, S4, S5, and so on and so on. So my first question to you is, what nice properties, if any, does this sequence have? Just sort of looking at the graph of it. What can we say about it that at least is, makes it not the worst sequence in the world to work with?
The limit, as n approaches infinity, is going to approach 1 and then negative 1.
Ah, okay. So let me write down what Matt just said. So the limit as n approaches infinity is 1 and negative 1. All right, so I just wrote that sentence up here. Somebody critique that sentence. What issues might there be, Patrick?
The subsets of the positive negative numbers.
Right, so Matt here is picking up on behavior that we'd like to make more precise, right? That for all of the positive terms in this sequence, it looks like the positive terms themselves have a limit of 1 as n approaches infinity. Meanwhile, all the negative terms, as n approaches infinity, appear to be approaching negative 1. Right? And yet the sentence, the limit of the sequence is 1 and negative 1, has a glaring problem. What's the problem with that sentence?
Limits are unique. Limits are unique.
Yes, exactly. The big problem with that sentence is that limits of sequences have to be unique. We can never say that a sequence has more than one limit. That was a theorem that we saw earlier in the chapter. So really the big problem with this sentence is right here, right? The word the, very first word in the sentence. Limits are, not by definition, but by theorem, limits must be unique. Limits of sequences are unique. That's something that we can prove. And so for that reason, we can never say that a sequence has more than one limit, right? Because in order to say that, just to go back to our usual picture here, we would have to be able to find one place, one value of L, let's say I put this L right here, such that for any epsilon that we choose, we can find a little n such that the sequence enters that bandwidth and never leaves for all n greater than or equal to n. Right? And if I set my limit at 1, then it's true that I can trap the tail of the top part of this sequence, top part, the positive terms, inside of that bandwidth past a certain point. But the problem is that we can't say that the whole sequence converges to there, because if we look at what the sequence is actually doing, every time the sequence jumps inside of the bandwidth, the next term jumps back out. So it's not possible for us to meet this criterion for convergence, which says that past whatever my n is, I need all of my terms, n greater than or equal to n, need to satisfy that Sn minus L is less than epsilon. So we would need for all terms of the sequence to do that, but we can see right down here that there are terms for which that doesn't happen. Right? So it's problematic for this sequence for us to speak about convergence, because convergence is a property that has to apply to the entire sequence. Right? So uniqueness of limits is our issue. The good news is that, well, we aren't able to say that the limit of this sequence is 1 or negative 1. In fact, well, we won't be able to say that this sequence has a limit at all. We do want to package that intuition that you see when you look at this graph that Matt was telling us about, that somehow there's a part of this sequence which converges to positive 1 and a part of this sequence which converges to negative 1. And so that's where subsequences come in. So here's my sequence. And what I'd like to do is I'd like to be able to somehow construct a new sequence out of this that contains just the positive terms. That's my goal. Now, the first of those positive terms was the second term in my original sequence, S2. Right? The second one was the fourth term in my original sequence. After that was the sixth term in the original sequence, the eighth term, and so on and so on. And so if I want to talk about just the positive terms in this sequence, what I really want is not all of the SNs, but just S2, S4, and so on. S4, S6, S8. So what I'd like to do is make a new sequence that only contains those terms. And for my new sequence, this would be, let me call the new sequence A, A1, A2, A3, and so on. And so then this new sequence would contain only these positive terms. And we wouldn't have these negative ones in here to rain on our parade, right, when we go to try to show that it converges to 1. So what we've really done is we've really taken selectively a small list, not small, I mean it's still infinite, but a sublist of all of the indices of my original sequence. So what we've kind of done is we've said the first term in my new sequence is going to be term number 2 from the original. The second term in my new sequence is the fourth term in the original. The third term in my new sequence is the sixth term in the original. The fourth in the new sequence is the eighth in the original. So what would the, let's call it the kth term in my new sequence be in relation to my original? 2k, right. So very often, this is how we'll write, this is the kind of notation that we'll use when we're extracting now what we call a subsequence, is we're going to say, let's let, one of the things we might do is we might say, let's let n sub k equal 2k. Then, and this is where analysis gets a bad name sometimes, then S sub n sub k, yes, it's a subscript of a subscript, is the subsequence highlighted above. Right? So S sub nk, or S sub 2k, is the sequence consisting subsequence of the original, consisting of just these terms that had the positive values. So when you look in the definition of what a subsequence is, it's a little bit opaque of a definition when you first look at it. Because the definition kind of says that what we're doing when we construct a subsequence is we're choosing an increasing list of indices. In this example, our list was the second, the fourth, the sixth, the eighth, the 10th, and so on. Right? And those are the values of n that we're choosing from our original sequence. And then the subsequence becomes S2, S4, S6, S8, and so on. Okay? So that's a subsequence of the original. Right? And what we can then say is not that the whole sequence converges to positive 1, but the subsequence S sub 2k does converge. Converges to positive 1. If we wanted to prove that, all we would really need to do, I think, is just write out the expression for what is S sub 2k. If Sn was n times minus 1 to the n over n plus 1, then just substituting 2k in the place of n should give away a nice expression for the 2kth term in this sequence. How can I simplify what I have right here? We could divide by 2k to get the k's just to be over here in one of the terms. But I'm really more interested in the simplification that will tell me that I actually got all of my positive terms and none of my negative terms. What is negative 1 to the power 2k? always positive 1. After all, we could rewrite it by moving this parenthesis here. We could rewrite it as negative 1 squared to the power k. And what's negative 1 squared? But 1. And 1 to the k is also 1. So that's the nice thing about extracting this particular subsequence, is now we have a subsequence that consists only of positive terms. And then we could use our usual definition of convergence to show that this is, in fact, a convergent sequence as k approaches infinity. So we've discovered a convergent sequence inside of a bigger sequence which bounces back and forth and doesn't converge at all. So here we have now, on firm foundation, a subsequence of this original sequence which converges to positive 1. By the same token, we can also say that there is a subsequence that converges to negative 1. And how would we write, what would be a way to express which subsequence that is? Yeah, here we just want all of the terms with odd indices, right? Starting from S1, and then S3, S5, S7, etc. I guess I kind of got that off a little bit just based on what's on the graph here. This is S5, this is S7, S9. Right, so all of the odd index terms from this sequence, that subsequence converges to negative 1. And if you are interested in why, again, we would just substitute 2k plus 1 into the formula for Sn. And then this negative 1 to the power 2k plus 1 would turn into what? Negative 1 for all values of k. And then we could show that this converges just using the definition of convergence. So subsequences are a convenient way for us to kind of split up a sequence that might have some bad behavior and find some pieces inside of that sequence that might have better behavior, might have convergence properties. And subsequences turn out to be a really useful tool because no matter how nasty a sequence can be, we'll see that there's some theorems that tell us that it will almost always, under reasonable assumptions about the original sequence, it almost always has subsequences that we can say something nice about. Right? It's like a crazy family, but at least we can find one good person to talk to inside of it. Right? So that's kind of where we're going on a philosophical level with this.